Position time graphs are going to be helpful for us to understand how things are moving, as well as being able to understand what it looks like graphically for things that are in motion. Some important ideas to understand with position time graphs. First off, our x-axis is our origin. That's where zero position is. And again, that's something that we can choose, but we don't have to necessarily understand exactly where that is right now. Anything that is up here then is going to be in the positive position region, right? And this would be the negative position region. So we can think of this as like our number line. The positive side would be here, our negative side would be here. If we look at a few different motions on a position time graph, first, this one is going to show something that has no motion. And it has no motion because its position, which maybe is +7, isn't changing. So a flat horizontal line is going to show something that has no motion. Another graph would be something that looks like this. This is somebody who started here as their initial position and moved in this direction into the positive region when they passed the origin. This is something that shows constant velocity. This would have a positive velocity, where a second example would be if something started here to that would be a negative velocity, but also is constant. Now, how can I know that these are showing constant velocity? The main thing we have to understand is, what does the slope of a position time graph tell me, right? So if we take these angled lines and we find the slope. Remember, slope is rise over run. That gives me my slope, which is this. Well, this is an initial position, or it's a position that we are taking our rise from, and we rise from this position to there, which that is my final position. So if we go from, that's like saying I started here and I went this way. How far did I go? That is my rise. So in terms of slope, slope is rise over run, which in this case, my rise is going to be my final minus initial. Whatever this value is minus my initial position, over my run, which is from this time to this time final. So that's how much time takes place, or a change in time that took place. What that shows me is that is displacement over time. And so my slope on a velocity time graph is my velocity. Excuse me, on a position time graph is my velocity. So I can say that this shows a constant velocity because it has a constant slope. And it's a positive velocity because it's a positive slope. This is a negative constant velocity. It's a constant slope, but it's in the negative direction. I forgot to mention that this also shows no motion for the fact that when we have a flat line like this, the slope is 0. And a slope of 0 tells me that there is 0 velocity, so it's not moving. Let's take a look at some other forms where we don't have a constant velocity. Two instances would be something moving in the positive direction, one that looks like this. That is a increasing slope. So that is showing something that is actually speeding up. Another example could be something moving in the positive direction, which looks like this. This is a decreasing slope. It's getting flatter. So that is showing something slowing down. Because remember, the steepness of the slope tells me my velocity. The bigger the slope, the steeper it is, the faster it's going. Our last examples with slope are going to be something moving in the negative direction that doesn't have a constant velocity. So one example would look like this. What we see here is we see our slope. This would have a slope right at the beginning of 0, right here. It's almost flat. And then we get steeper and steeper and steeper, right? So that is showing an increasing slope, which is speeding up in the negative direction. The other example would be something that is still going in the negative direction, but is slowing down. Notice here, our slope is 0 here. It gets to 0, where we have a steep slope here. So this is showing something that has a decreasing slope or slowing down. One mistake we want to try to make sure we avoid is that time is always moving to the right. So our graph can never look something like this, because this would indicate that we went forward in time and then we went back in time, which is not possible. So time always moves to the right, so our graph always has to be moving to the right in some fashion. Even if I were to stop, right, the points that I would be at would be increasing to the right because time is moving on. So some other examples that you'll see, maybe a graph that looks like this. This shows something that is moving in the positive direction, but it's slowing down because it's getting to a point where my slope is 0, right here. Really, a better representation would be m equals 0, right there. So it's going in the positive direction, but slow down. And then it starts moving in the negative direction and it starts speeding up. My slope is going from 0 to a steeper. Opposite of that, if we have something that's moving like this, this is, again, slope of 0 here, so that's where it stops. This is slowing down in the negative direction, slowing down. This is speeding up in the positive direction. You might also get something that looks like this, where we have something that is slowing down in the positive direction for the first part. We get something that maybe stops or really close to stops here because our slope gets really close to 0. And then it again speeds up in the positive direction. So this object never actually changes directions, right? It just slows down and speeds up. Whereas these two, this one here and this one here, are actually changing direction. They're going from the negative direction, a negative slope, to a positive, or a positive slope to a negative.